Hello, thanks for coming. I will talk about tracing today and some of the upcoming features actually coming up in Go 1.11. But first of all, I want to give a little bit introduction about myself. I'm using Go as a primary language for a long time now, and I also worked on the Go team for a couple of years. And currently, I'm working on mainly latency analysis projects at Google, and mainly focusing on Go. So the title says tracing, and I want to start with giving a little bit more context about what tracing is and why do we trace. This conference is about programming, so I think that it's an appropriate place to talk about pipes because pipes are the greatest analogy for anything pretty much related to systems. What you're looking at right now is a network of pipes. To be specific, these are water pipes. These are the connectors of different components. That allows us to transport water from one place to another. Have you ever thought about the healthiness of such a system and how to measure it? Maybe to begin with, what is the healthiness of a system? If the whole purpose of our system is to carry some water from one place to another, maybe we can measure it by measuring how well, whether we are carrying enough water from one place to the other from the user's perspective. So how efficiently we transport the water is another topic, and it's more about optimization. Firstly, we want to be able to focus on the functional side of it rather than thinking too much about the premature optimizations. So I want to make sure that this is not a talk about performance. It's more about we're not trying to improve the performance of the water pipes or anything. We're just trying to understand, debug the unexpected problems first. So there are various factors that may cause our system to have an outage. For example, a pipe could be clogged, or a pipe might be leaking or not pressurized enough as we expected. Both of these issues are affecting the throughput of our system. And what is the path and direction of the water, right, until it is served at the endpoint? We can easily diagnose what components are involved in an outage by answering this question. What if the water is leaving some hints behind as it's following through these pipes? So we can generate the flow path by looking at these hints and see the actual path and direction. Tracing allows us to see things end to end, and until we serve to the end user. It can be water, it can be a function call, it can be an HTTP request. The basic principle is usually the same. Trace subcomponents to see what is happening end to end. That impacts the end user. So healthiness is also about availability. We as an industry usually just underestimate and use just a percentage value when we're talking about availability. But how practical is it? For example, 100% availability is unfortunately a lie, right? In any system, it's so complex and so expensive to achieve 100% availability that it's actually not practical, and it's not worth to achieve it. What is good enough availability then? Or maybe we should ask what availability is. Availability is about whether a service is performing as the user is expecting or not. But if it was unavailable only when the user was not looking into it, would it be still considered unavailable? It sounds like a very particle duality case for a second, but availability is really what would give user an experience that it almost feels like they're, even if there's no outage. In the simplest terms, we say that service is available if the users cannot tell if there's an outage. So, you can have outages, but failure can happen, but it should be rare enough. And it depends on your business case, really, and how much failure your users can tolerate. The key here is not to maximize the availability. It's not about trying to hit 100%. It's a waste. So your teams has to have a principled way of communicating what level of downtime is acceptable, we use this methodology to define and communicate it all across our organization. We call this methodology service level objectives, or SLOs. And there are two main categories of measurements we care when we are defining and setting SLOs. The first one is, what is the acceptable error rate? And the second one is, what is okay in terms of latency boundaries? We usually say we usually put goals like, hey, 99.99% of the requests will return less than 100 milliseconds. Or, similarly, we set some expectations for throughput for batch processing services. So tracing can be done to trace the execution in a single process, or actually it can be distributed where many processes are involved. This is an example of a trace visualization. And you're currently looking at a distributed trace at request RPC level. What user experience here is this 300-ish milliseconds of latency, but as the operator of the system, if you have distributed tracing rolled out, you can easily see what happened internally in that 300-ish milliseconds. It looks like we're jumping among multiple services until we respond. So user in this case is getting slash messages endpoint. Internally, it actually requires 4 other calls. Each yellow box here is representing a call. We check the integrity of the request first, and then we see if the user is authenticated, that out access token call, and we do some cache lookup. And I think there was a cache miss that we queried our database to retrieve the results. And you can see how long it took each sub-component to respond. And again, more importantly, what components were required to respond to this request. This is what tracing instrumentation and visualization tools allow us to see. Or in this case, it took 245 milliseconds, but your customer is on the call maybe, just yelling at you saying that, hey, I couldn't get this API working. It's responding to me with HTTP 500, and there are no other further error messages. We can easily take a look at our distributed trace and see what happened, because we internally usually collect more information with our traces. So if there's an error, we usually collect the error message right there. And it looks like from the error message that we were sending a malformed payload maybe to the cache server and it was failing. We can fix the bug and then redeploy the service and it will be all fine. This was actually what happened to me when I first joined Google. I was so nervous to work for a large company after working for small companies for so many years. But on my second day, I fixed the bug and we pushed it to prod at that week. And I did it by simply looking at our distributed traces. There was so many more services involved in my case, and there was no possibility that I would read millions lines of code and docs to understand the big picture and narrow the issue down to a specific RPC handler. So I want to talk a little bit about latency. We said there are 2 critical measures. The first one is whether we are serving to our users without errors or with the error rate we promised. The second case is, the second measure is whether the latency is in this expected range. So both are critical to tell how well a system is doing, but latency issues are very hard to pinpoint, unlike the previous case of detecting errors. And we benefit a lot from actually tracing to understand underlying causes when it comes to latency. What causes latency? Who knows? It's too complicated. There's always too many moving parts. Network outages, scheduling, poor utilization, GC, computationally very expensive libraries you've just rolled out, you name it. So how does this all relate to Go? Go has become the language to write service nowadays, so we celebrate it. Yay. But and to face the reality, at any time, there are tons of independent requests that are going through, an average Go server. And they're interacting with, and depending on common components such as the runtime, and affecting the overall, the state of the things. So they are not actually as independent as I just claimed. So the activities are occurring during the program execution are, stuff like scheduling, memory allocation, and garbage collection. And it's very hard to associate a request with its impact on the runtime, and runtime's impact on the request. So let me go back to this pipe analogy for a second. By using our latency metrics or distributed traces, maybe we can narrow down the problem and say that, hey, this service might be the problem, but it just doesn't give us any further details. It doesn't help us, further to investigate what might be the cause. And if a pipe is clogged because of a runtime event here, we should be able to understand the case and address it with an optimization if it's really repeating and it's critical. This is a very common feedback we get from our SRE. They're saying usually, hey, there's no easy way to tell why latency is high for certain requests. Is this garbage collection, scheduling, or some blocking calls? Can you just review the code and help us? Come on, nobody is actually equipped enough to digest lines and lines of complex relationships and code to tell how to optimize. We need a better diagnostic solution. So I want to enter the world of the Go execution tracer just a bit. This tool has been around for a long time. It has been contributed by Dimitri Yukio. He rewrote the Go runtime schedule, so he built this tool basically to debug, his work. And it's the current de facto tool to diagnose Go runtime. It does two things. It reports fine-grained, runtime events from a Go routine, and it also can report the utilization of CPU cores. But it cannot tell, if your specific code is associated with some runtime events. It just cannot tell. And under high load, there's so much going on that it's almost practically impossible to isolate a specific request and see its impact. So I will go back to the previous distributed trace, and I want to focus on this handler access token for a second. Assume that 172 milliseconds is an unusual latency for this span. We haven't figured out yet, what might be the cause. We just know by, looking at our, historical data that this is unusual. It probably knows. There's also some metric collection somewhere. It just, alerted us that hey, there might be a problem or an SLO violation. So we confirmed that there's no host or network-specific incidents, affecting this service. One of the other things that we want to take a look is let's take a look what is going on in this process. So we just want to, get more data from execution tracer to see what is going on. Execution tracer is adding a new feature in 1.11 that allows us to mark sections in our code, and then it can simply break down how much time is spent on what. On these sections during the execution. So the handler here, if you can see from the transparent boxes, it's executed and then preempt and executed and preempt. With 1.11, we will be able to generate a report where that time is spent in those boxes, where the time in those boxes is spent on. So here, there's an example about one box. We did some networking, 6 to 8 microseconds, and then we executed the handler just a little bit, probably, for serialization and deserialization. So there was nothing, blocking. It was the handler executing. And then we waited on some blocking syscalls for 5 microseconds in this case. And then we had some garbage collection. And it blocked us for 8 microseconds. So execution tracer is not just going to report us this latency details. It will be also, be able to visualize the overall flow of the execution. The purple boxes here are when the access token handler is being executed. It's been momentarily blocked by I/O, waiting on an ePOL, and then execute it for a while, and then a syscall happens, that small red block, and then it executes a little bit more, and then bam, there's a GC, things stopped, I guess, and then executes more, and then does more I/O and finally finishes. This is great data to watch for repeating patterns and addressing the anomalies in a very fine-grained way. So this sounds good, but how do we do it? The standard libraries runtime traces introduce new APIs to mark sections, and execution trace is extremely expensive to keep it on all the time. We enable it only when there's a problem, and we want to diagnose what is going on, record some data, and then disable again. And then we will use the regular execution tracer tool with the new UIs to visualize the recorded data. So there are 3 new concepts we added to the standard library. These are regions, tasks, and annotations. They allow you to mark sections in the code, in your code base, with names, and allow you to also log important events. The runtime can now associate these sections with its own events. If a runtime event is triggered because of your code, it associates them and can do accounting and report all these different metrics and latencies. So it can be also used with distributed traces. It makes it possible to go and dig into an RPC handler when things are unusual. Let's talk about a little bit of the marking sections. So we expect you to mark your code. It requires some manual instrumentation by starting and ending things. So we have 2 kind of markers. The first one is the region, and the other one is the task. This is how you mark a task. Basically, new task begins a task, and then task end is ending it. And you need to write the code in between. It's very similar for regions as well. And let me explain why we have 2 different types. Regions are the sections of code that doesn't span among multiple goroutines. So you need to start them and end them on the same goroutine. Otherwise, execution tracer cannot do the accounting and giving you the fine-grained details. And then we have this logical group called tasks. If you want multiple regions to be clustered under the same thing, you can start a task, create regions under it, and then you can search for a specific task and see all the regions grouped under it from the UI. It's great for clustering and querying. For example, if you start a task for an RPC handler, you can add fine-grained events happening under that handler as regions. And the restriction here is just the tasks can start anywhere and end anywhere, but regions shouldn't cross goroutine boundaries. Task 1 is here starting at goroutine 1 and ending at 5, I guess. But regions, all the regions here are starting and ending on the same goroutine. So I'm not sure if you have used the execution tracer before. In order to enable the tracer and collect, there are multiple ways, but I'm going to show you registering the trace handler to the default mux by importing this net HTTP pprof package, and then you can start an HTTP server at 6060. In my case, I was working with a gRPC service, so I didn't care using the default mux. And after making this handler available, I can curl this endpoint, and I'm enabling collection for 5 seconds here. Downloading the collected data and using Go tool trace, then to visualize it. If you have used this tool before, it starts a web UI, which doesn't have the best CSS in the world. So this is one of the new pages added to the UI. In a demo program, what I did is actually marking all my gRPC handlers. I have some sort of a middleware that creates a task in the beginning and then ending it in the end. So this is what execution tracer collected for the gRPC Hello World server. The Hello World greeter, say hello, is a handler. Is my handler, and you can see the duration, the distribution of the completed handlers. There are 312 tasks because I made 312 calls to this handler, to the endpoint. And you can see that there are a few 100-millisecond outliers. I just want to see, what happens. So you can click on that link, and then it's taking you to the details. Once you click, this is what the UI is actually taking us. This is sort of like annotations. Again, the CSS is just not very great, and I'm not sure if you can see, but this is where you see the significant events and annotations in the lifetime of a task. And we can see that our PCs have overlapped with some garbage collection. I think the task, for example, 176 spent some additional time in garbage collection before it's finished. And it had to probably spend more time on scheduling, so that's why we ended up having slightly slower handlers than the others. So as I said, each task can have multiple regions, and we have another UI page for that. In this case, we have 5 regions related to, say, hello, RPC. And there's another region related to runtime timers bucket, the first one. So let's avoid it for a second. And you can see the distribution is, again, duration distribution is represented, and you can click and to any distribution bucket to see the details. And this is actually where the things are getting more exciting, because, as I said, regions are supporting accounting. They can actually tell us where the time is spent on. So no more guesswork, no more trying to worry about how runtime tweaked the results. We can see clearly and explicitly what happened. In this case, we're looking at this region called con.ready, and you can see how much time they have spent in execution, network, sync block, syscalls, scheduler wait, and garbage collection. And if there's an outlier region, you can understand why it's an outlier again. You can optimize if it's recurring and if it's critical. But if it's not violating any SLOs, or if it's not an issue, you can ignore as well. It might be just some noise. So there are a few other UI changes that allows you to visualize the call chain, but I'm not going to give so much detail in this talk. Rather want to focus on high-level aspects. You usually want to collect this type of data in production because you need to have an incident. But it's extremely expensive to keep this on. So we recommend that turn it on momentarily. As I said, you can use the trace handler, or you can use the runtime tracers, other starting and stopping APIs. And then grab the data and then use the Go tool trace to visualize. So these features are going to be in the upcoming release of Go. If you want to try it right now, I highly encourage you to do so. But for now, you need to install Go from the source or wait for the first release candidate to be released. I think it was supposed to be yesterday, but deadlines are a lie. So. If you also want to see an example usage with distributed traces, I actually added some support for the execution tracer tasks to this library. Once you create a distributed trace span, it automatically creates a task, and then you can add some regions, and then you will be able to see all the regions are represented under your span name / messages in this case, and then you can easily correlate them with your distributed traces. So unfortunately, nothing is perfect, and let me give you some spoilers. We have some limitations. Regions, the first thing that I actually mentioned, the regions need to start and end on the same goroutine, so we cannot easily do accounting for everything automatically. You need to still, manually mark sections and make sure that they are not crossing any goroutine boundaries. We need to work hard on, manually instrumenting RPC frameworks and, such as gRPC and some HTTP libraries, including the standard library, NetHTTP. So that's our future work. At least, we're planning to do that work, and it's good news. The other thing is the export format. It's this format that Go Trace tool uses, which is not a very easy format to work with. So you cannot easily, convert that format to your existing distributed tracing visualization tools format, and attach that data and represent it over there. So you need to collect the data, and then you need to visualize it with this separate tool, Go tool trace. It's a little bit tedious, but probably it's okay for now. Even though these limitations, I think this is a good addition for those who is maintaining Go in production. And especially with the accounting available now, we have more visibility into our prod and actually can take action when things go wrong. Being able to understand there is latency but having no insights was not that ideal. This is where Go is trying to improve, and the future work is, I think, very exciting. I just want to say, questions and comments are welcome. Bugs are also welcome at this point. Try it before 1.11 release and file some bugs. Thank you very much again.